faithfully delivering value, interpreting great books from around the world. Hello, this is Sally's Book Club. Today we're exploring the book A Thousand Billion Suns. The sun is a star, so 1,000 billion suns means 1,000 billion stars. The sun is our most familiar star, close to Earth, providing astronomers with abundant observational data. At 4.5 billion years old, the sun is in its prime, stable, luminous, and full of vitality. Using the sun as an example, this book illustrates how stars navigate their life cycles.
The author, Rudolf Kippenhahn, was a German astronomer who served as professor at the University of Göttingen and later directed the Max Planck Institute for Astrophysics. It's possible in this case.
He authored several astronomy works like Stellar Structure and Evolution and Light from the Cosmic Abyss. This book, A Thousand Billion Suns, adapts the author's lectures, more approachable than technical texts. Not overly technical. Setting aside complex formulas, he vividly depicts stars' lives from birth to energy-depleted death. In this discussion, I'll first guide you through stellar characteristics and states. Then we'll explore how a star journeys through its lifetime. So, what defines a star? How does it differ from other celestial bodies? As the saying goes, all life depends on the sun. Earth's existence relies on solar energy. This distinguishes stars from planets. The star's defining trait is sustained energy release through self-combustion. Take our sun. It radiates 10 to the 23rd kilowatts per second, yet Earth receives merely 200 trillion kilowatts, a tiny fraction. Earth absorbs solar energy by day and releases most residual heat at night. Some energy chemically stores in plants via photosynthesis, converting water and CO2 into organic matter. Humans and animals depend on this plant's stored energy for survival. Fossil fuels like coal and oil originate from ancient buried plant energy transformed over eons. So, where do stars themselves get their energy? This originates from nuclear fusion inside stars, where lighter atoms collide to form heavier ones.
During fusion, a tiny bit of mass is lost while releasing enormous energy.
Einstein's mass-energy equation, E equals mc squared, explains this. The lost mass multiplied by light speed squared equals the energy released. 1 gram of hydrogen fusion releases 630 billion joules, 20 million times more energy than burning the same weight of coal. Another stellar trait is their finite lifespan. Stars can't burn forever. They undergo birth, prime, aging, and death. After death, stars transform into new cosmic states, while planets like Earth get consumed during their sun's aging. Now I'll guide you through a star's life journey. First, how do we determine if stars among billions are young or old? Stellar lifespans range from millions to billions of years. Tracking one star from birth to death is impossible for humans. It's like a fruit fly with its 30-day lifespan trying to observe a human's entire life. But if that fly could photograph all humans instantly, it'd see children, adults, and elders, piecing together life stages. Similarly, we catalog known stars, categorizing them to understand different life phases, thus reconstructing a star's life. To determine age, astronomers use two measurable metrics: surface temperature and luminosity. How do we measure stellar temperature? Astronomy uses color temperature as a measurement method. Objects emit different colored light when heated to various temperatures. Like heating iron. It glows red, then yellow, and finally white as temperature increases. So conversely, we can determine a star's surface temperature by its color. Higher temperatures shift star colors from white to blue. Lower temperatures make them redder. Luminosity represents a star's total energy output. What we see as brightness depends on distance. Distant stars appear dimmer. By measuring apparent brightness and distance, we calculate true luminosity. Luminosity relates to mass. Higher luminosity means greater mass. With temperature and luminosity, we classify stars. Imagine a coordinate system. Horizontal x-axis shows surface temperature. Rightward means cooler. Vertical y-axis shows luminosity. Upward means brighter and more massive.
Every star occupies a position here, forming astronomy's most useful relationship.
The diagram was independently developed by Danish astronomer Ejnar Hertzsprung and American Henry Norris Russell. Named using their initials, HR diagram or H. Hertzsprung-Russell diagram, to honor their contribution. We've included this diagram in the notes below. When plotted, stars naturally group into three areas. 90% form a smooth diagonal curve from top left to bottom right. The rest scatter in top right and bottom left. Curved stars are main sequence normal stars. Top right stars are luminous and massive. But cooler and redder, these are red giants or supergiants. Bottom left stars are hot but dim and lightweight, white dwarfs. Main sequence stars are like young adults, shining for billions of years. Red giants and supergiants, though huge, shine far shorter, like middle-aged humans, while white dwarfs, small with fading heat, resemble the elderly. Like humans in their twilight years, a star's life cycle is thus revealed through the HR diagram. Unlike fruit flies, we humans can simulate stellar evolution via computers, then verify observations against these models. I'll now guide you through a star's life in 3 acts: birth, aging, and death. First, how stars are born. The vast interstellar space appears empty.
But actually teems with gas and dust.
Gravity pulls these particles together like cosmic dust bunnies, forming a speck emerging from the void. This nucleus snowballs, attracting more material as it grows. Over millennia, infalling gas increases core density until it turns opaque. Initially, collision energy radiated freely into space.
But opacity traps this energy, causing core temperatures to skyrocket.
Imagine covering a heater. Trapped heat makes everything hotter inside. Meanwhile, the core's composition undergoes radical changes. Primordial gas consisted mainly of hydrogen atoms. Hydrogen gas is building blocks. Colliding hydrogen atoms formed molecules as temperatures kept climbing. At 2000 degrees Celsius, molecules shattered back into individual atoms. When temperatures hit 10 million degrees, fusion ignited. 4 hydrogen nuclei merging into helium. At this moment, a star is truly born. Why does fusion mark a star's official birth? Because fusion allows self-sustained energy production. No more snowballing needed. The star becomes a radiant giant. Unlike solid Earth, stars are gas balls from the moment they're born. This happens because stellar interiors are so hot that atoms shed their electrons, leaving nuclei and electrons freely zipping through the star's core. This creates 2 key outcomes. First, electron-stripped nuclei take up far less space, making stellar cores incredibly dense. Second, since nuclei and electrons can't settle, the star remains gaseous. But wouldn't a gas ball just expand or collapse?
That's precisely what stars maintain between birth and old age.
They achieve internal equilibrium to keep their size constant. Picture a heavy piston sealing a container from above. Gravity and gas pressure balance the piston, just like stellar equilibrium. Inward gravity and outward pressure balance perfectly. Without pressure, everything would collapse inward.
Without gravity, pressure would blast all matter into space.
So, that addresses our first question. How is stars born? Interstellar gas and dust snowball under gravity's pull. When enough mass gathers and temperatures soar, hydrogen fusion ignites. A star is born. After birth, stars live stably on the HR diagram's main sequence. Our sun has shone steadily for 3.5 billion years and will stay on sequence for another 4 billion. With minimal visible change, time on sequence depends on mass. Heavier stars burn faster. Leaving the main sequence signals aging begins. How does this aging unfold? Depleting core hydrogen marks a star's entry into old age.
Astronomers simulated our sun's aging. Let's explore that process.
Recall, stars fuse hydrogen into helium at their cores, releasing energy. We can vividly describe this process as hydrogen atoms being burned up. When the sun's core depletes all its hydrogen, it forms a pure helium nucleus, while the outer shell remains hydrogen-rich. At this stage, the helium core hasn't ignited yet. Helium fusion requires even higher temperatures, but fusion continues at the core surface, the boundary between helium and hydrogen layers. Helium produced by hydrogen fusion merges into the core, increasing its mass steadily. As the helium core grows heavier, its gravitational pull intensifies, causing inward contraction. To counterbalance this, the sun's outer shell expands, cooling its surface and turning it red. Thus, the sun becomes a red giant, shifting to the upper right corner of the HR diagram. Astronomers estimate this transition will occur around 13 billion years after the sun's birth. The aged sun will be 100 times larger and 2,000 times brighter, with surface temperature dropping to 4,000 degrees Celsius. Ha! 1,800 degrees cooler than today. What then for Earth? No life could survive. Heavier stars age faster. The greater the mass, the sooner senescence begins. Take Sirius, the night sky's brightest star. Twice the sun's mass, yet its prime ends in just 1.25 billion years. A star 10 times solar mass occupies the upper main sequence but may last only 10 million years. Heavier stars undergo more complex aging. For stars over twice solar mass, their shrinking helium cores heat to 100 million degrees, igniting helium fusion into carbon. Helium fuses into carbon, turning the core into a carbon sphere. Stellar composition layers, hydrogen-rich outer shell, a helium layer beneath, and a buried carbon core. During aging, mid to high mass stars exhibit periodic pulsations. Pulsation means stars act like balloons, expanding and contracting. How does that happen? It relates to the star's outer shell. Like our piston example, pressing down increases pressure, forcing it back up. Without friction, compression energy returns during expansion, creating a cycle. The piston oscillates around equilibrium. Stellar pulsations work similarly. When gravity compresses the star, gas pressure rises.
But compression heat can't escape the outer layers, making pressure exceed equilibrium levels.
So pressure forces the outer shell to overexpand.
At maximum expansion, material becomes transparent, releasing excess radiation, reducing pressure and letting gravity dominate. The shell contracts, repeating the cycle. To observers, this creates rhythmic brightness pulses. That answers our second question: how stars age. Aging begins when core hydrogen depletes. Stars expand, cool into red giants. Heavier stars evolve further. After helium fusion, carbon cores form and undergo pulsations. In short, heavier stars age faster and more complexly. After aging, how do stars meet their end? As noted earlier, stellar mass determines aging paths, and different masses yield different deaths. First, our sun, becoming a red giant in its twilight years. Dying, the sun will eject its outer layers into space, leaving a white dwarf core too cool for fusion.
Stars between 1.4 and 10 solar masses develop carbon cores.
Its demise can unfold in two possible scenarios. First scenario, the carbon core's temperature keeps rising toward fusion ignition point. But extreme heat causes charged particles to merge into neutral ones, cooling the core.
This prevents carbon fusion. When ignition finally occurs, the long-delayed reaction explodes violently, shattering the star.
Alternatively, in carbon core stage, extreme density may form a white dwarf. Fusion halts while outer shells keep burning, transferring mass inward. Higher density means stronger gravity. Ultimately, immense gravitational energy violently ejects stellar material, creating an explosion. Astronomers call this a supernova explosion. Supernovae can brighten by tens of millions within days. Around 1054 AD, Chinese and Japanese records noted an extraordinarily bright star, visible even in daylight for 2 weeks. Astronomers believe this was a supernova event. The remnant white dwarf collapses within minutes into a neutron star, second only to black holes in density. For stars over 10 solar masses, death comes through iron core collapse. After carbon core formation, evolution intensifies. Carbon fusion produces magnesium, oxygen, neon, sodium, diversifying elements, but fusion halts at iron, nature's stopping point.
'Cause fusing iron nuclei consumes energy rather than releasing it.
Thus, massive stars develop gaseous iron cores. Iron nuclei capture free electrons, removing the pressure source. Gravity dominates. The iron sphere collapses until protons and electrons merge into neutrons, forming neutron matter. The star becomes a neutron star. This happens rapidly, Outer material can't withstand the energy, triggering another supernova that leaves behind a neutron star. Well, neutron star? If a star has too much mass left when nearing death, unable to form a white dwarf or neutron star, it collapses inward under gravity, becoming a black hole, an object even light can't escape. Ultimately, whether stars become neutron stars, white dwarfs, or black holes, they transform into ultra-dense objects lingering eternally in space, a cold, bleak future for nearly all stars. Yet their vast outer shells return to interstellar space, becoming raw material for new stellar generations. Third question, how do stars die? We've covered varied fates by mass. Our sun will scatter its outer layers when dying. Its core forms a white dwarf. For stars with final masses between 1.4 and 10 solar masses, there are two outcomes. Their cores become carbon spheres, either exploding or evolving into neutron stars. For those over 10 times solar mass, iron core collapse may occur. After carbon core formation, fusion continues until iron forms, collapsing into a neutron star's core. The material explodes back into interstellar space. That summarizes 1,000 billion suns. Published in 1980, stellar research has since advanced. Probes reached Neptune or Pluto, and Kepler telescope captured a supernova's full process.
Ongoing observations and simulations have largely confirmed astronomers' stellar life cycle models.
Understanding stars reveals Earth's fortune. Its perfect solar distance keeps oceans liquid, neither frozen nor evaporated. Life emerged, and the sun's ideal age allowed single-celled organisms to evolve into humans over eons. Among billions of stars, some may host their own Earths. This makes us believe other intelligences exist beyond Earth. Stars are born from stardust, and to stardust they return. Over billions of years through atomic furnaces blazing, they've nurtured countless lives. When you next gaze upon the vast, mysterious cosmos, do you feel deeper kinship and reverence? All right, that concludes our journey through 1,000 billion suns. Study notes are below the audio. Until next time,